Okay. So please, Dmitry, the stage is yours. So
Okay, thank you very much. And yeah, good afternoon. Hello, everybody. And first of all, I would like to thank SRF for this option and opportunity to tell about our CRG beamline. For those people who regularly watch this webinars, you know that there are two types of beamlines at ESRF, and I actually belong to this collaborative research group, Swiss-Norwegian beamline. I'm not going to give you many details about the technicality of the beamline, flux, etc. I think the best illustration would be just to show what we're doing. And if you go to good laboratory X-ray facility in any university, you can find basically four main machines. Single crystal diffraction, powder diffraction, scattering from surface, small angle scattering maybe. And when you go to synchrotron, you of course find the same thing, but in much, much larger scale. And the normal logic is that if we can't solve the problems with our laboratory equipment, we write proposals and then we go to the synchrotron. In reality, actually, the distance between these two is huge. And there is a lot of room between laboratory and synchrotron devices. And this is exactly where we actually try to do our science. So BM01 beamline of Swiss-Norwegian beamlines at ESRF combines 4 diffraction techniques in one device. We can do single crystal diffraction, normal break data acquisition, we can measure diffuse scattering, we can do high resolution reciprocal space mapping. Of course, the same can be done with the powder diffraction, either in the high resolution or high intensity mode, and the time resolved diffraction within the flux density which is available to us, it's sub-second. We have two detectors, therefore we can do also small angle scattering, better to say diffraction at small angles because our flight path is about 3 meters. And more we have surface scattering in the grazing conditions or in depth scattering. All these techniques can be used separately or in a combination, also with a variety of in situ and operandi regimes. So equipment which we have is basically a diffractometer with two detectors, a variety of goniometers. We have auxiliary in situ Raman and a lot of tools which can control and realize different conditions on the sample. And this is something which we consider as very important. Look at this collection. So what we have, some of them are commercial, they are designed at the beamline or at the post beamlines, let's say. And I will try to show this example how the development of new tools open new possibilities for our users. Charles McMonagle is our beamline scientist who specialized in the sample environment and enthusiastically developed new things. The data which we measure, conceptually very simple. We measure intensity as a function of scattering vector and as a function of time, external conditions. But if we look closer, then we see that for single crystal, for example, it's 3-dimensional data in the Q space. For surface, 2-dimensional. For powder, it's 1-dimensional. So the data are very heterogeneous. Moreover, the pathway from the raw data to the final information to the results, and this is actually what users want. So nobody is happy with just raw data. So this pathway is quite complex and has different stages, which you can call data processing and data analysis. There is sometimes very broad border between them, and this pathway is very different for single crystals, powders, thin films, and depends on what we want to get. It looks messy, and it's messy indeed, but we know this pathway very well, and we develop a lot of software tools which help users to get to the results as fast as they can, and also to organize the experiment in a friendly way, controlling the conditions from our software, and also making some complicated sequences of actions in the experiment. So we have a dedicated person, Vadim Detkin, our beamline scientist, who enthusiastically writes this software I have to highlight that most of the software tools are done in collaboration with users and for solving particular users' problems. That's how the project starts here. And at the end, it works quite well, I have to admit, and we're quite happy to see from the response from the users, which we receive from the user office, where they consider success of experiment above expectation. The other measure of the success at the beamline is the number of publications, but that you can check yourself at our website. Here I want to show you the result of USRF cross-cutting review on the energy-related materials, where you can see that our beamline actually does quite a big portion of the entire USRF outcome. Of course, it all looks like there is a certain magic there. There is no magic, and this I want to show you with just examples of research. And we start with something very, very simple, pressure. So the pressure also in relatively low range from 1 to 1000 bars, which can be done if you put your material, powder or crystal inside the sapphire tube and apply pressure hydrostatically with oil. And this is a device done by Charles. Why it's interesting, especially at synchrotron, where the most of the pressure measurements done with diamond anvil cells. So when you close diamond anvil cell, you have the pressure which can be twice higher than that. And for many industrially important processes, for the soft materials, you already have a lot of interesting stories which you miss. Of course, it's not just as simple as it's shown here. This device has to be correctly calibrated, tested, characterized, combined with the heating and cooling, with automated in terms of the pressure application and control, and also have to be modular in the sense that it can be combined with different techniques such as Raman or all the diffraction techniques which we support. So in the end, when we have such a device in the shell, we can study, for example, barocalorics. And this is one of them, how to say, old stories that people want to preserve food, all our history. And the barocaloric, they use the latent heat from the first order phase transitions induced by compressing and decompressing. So one of the very popular materials is NH4 iodine, which shows the giant barocaloric effect. And what happens if we put it in this pressure cell and the measure as a function of temperature or as a function of pressure at different temperatures? So you see the powder pattern looks perfectly okay, well resolved, clean. And you see the phase coexistence, you see the shift of the phase transitions, and you immediately can calculate the volume jump associated with these transitions and build up a phase diagram. From this phase diagram, immediately from the slope of the border between two phases, using Clapeyron equation, you can calculate the total entropy change. And from unit cell dimensions, you can calculate one of the components of this entropy change related to the phonons, which can be obtained if you know the thermal expansivity and compressibility, as well as the specific volume. All we measure in diffraction. So the simple calculations show that 45 of the total entropy change is due to the volumetric effect. And this is quite important information for the people who develop and optimize this sort of materials. So that is one of the illustrations of the complementarity of these in situ diffraction techniques to macroscopic measurements like differential scanning, calorimetry, and the pressure. So what we can do is a fast mapping of pressure, temperature, phase diagrams, calculate thermodynamical characteristics from diffraction data, derive microscopic scenarios of the phase transformation from structural analysis in case if we do rate refinement, for example. And it's also very easy to realize cyclic measurements and evaluate the stability and degradation of failing. group of users which are mostly focused on data are shown here. We have more experiments from other user groups, and those are just the first papers which appears and more to come. So they show how very simple device, or something which seemingly simple, let's say, don't look at the details, open new options and attract many users with the materials for the barocaloric and the like applications. So the similar example is about electrochemistry. So time ago, we developed our own operando electrochemical cell. The special thing about that is the single crystal sapphire windows, which more or less transparent for X-ray. And give very low background and make the entire cell very rigid, and all the results are very reproducible. Now the cell is copied and done at many places. So we never measure with one cell, usually it's a 6-cell array, and a small comment on the data. So the measurements are relatively fast per cell. So if we do charge-discharge cycle, which varies from half an hour to a few hours, in the end of the day, we easily have 1 terabyte. So this is something to keep in mind when we work with in situ electrochemistry. So what we can learn from such a data? From many examples, I actually selected one of them, which I like because it shows some, let's say, hidden feature, like the life of lithium in a carbon. If we just stop charging our battery, what happens there? So this is a lithiation of carbon, which starts in the beginning. So we form and evolve lithium C30 phase. At a certain moment, there is a transition to lithium C18. And at this point, we disconnect the battery. So, but we still keep measuring diffraction. And we see that there is quite big life for a few hours. The system changing. If we look closer to the detail of these changes, then from intensity of break reflections and their positions, using Kolmogorov-Avrami equations, we can identify 3 different stages with 3 different kinetics. The microscopic origin of the thing is, of course, redistribution of lithium. And a bit better insight we got from molecular dynamics simulations. What happens here is the following. We start from the disordered distribution of lithium ions between graphite sheets, and then with time we have more and more organized agglomerations of these lithiums into the certain groups, and at the end we have more or less stable state. So this is one of the results of the modeling. So you see the diffraction, and it actually resembles quite closely to what we see. And in the relaxation, in the end, we just have the formation of the groups of lithium in the galleries between graphite sheets. And this message is actually quite important because it means if we do ex situ measurements with a battery and we open it after at a certain stage of the charge, it's not what we have in situ, because there is a certain dynamics. The batteries are not equilibrium devices. When we stop something, there is a relaxation processes of the battery to reach equilibrium. And if we do, for example, a cycling protocol, the waiting time between cycles may easily give us very different results. Now I want to show you that not only hardware, but software and sometimes even ideas can also open new roads for the experiments. And I start with the diffuse scattering. And diffuse scattering is a very old topic in the diffraction. Basically, if you have a crystal with a disorder, the scattering density can be described as the sum of 2 components. One of them is periodic and the other not. And a Fourier transform of that, which we call structural amplitude, also will have 2 components. One of them is periodic and the other not. Intensity, in the end, will also have 2 components because all cross terms will go to 0. One of them is a break scattering and the other diffuse scattering, and that is what is reflected in the modern definition of single crystal from International Union of Crystallography. So the crystal is everything, which gives you break scattering, besides the always present diffuse scattering. However, interpretation of diffuse scattering is quite tricky. We know that it arises from correlated local deviation from the average structure. It contains information on the short range order, but how to deal with it is not easy. So the obvious way to solve the real structure, let's say, is to do real space modeling of disordered structures, something like Monte Carlo realizations, but there could be millions of them, and none of them is unique. Or we can do a Fourier transform of our diffuse scattering, and then we will have a sort of the Patterson function for the deviations from the average, the approach which is called now 3D delta PDF. And we're quite happy because the user who came to our beamline as a PhD student recently got as a professor a break prize from International Union of Crystallography for development of this technique. However, it is still quite difficult business. Case-to-case analysis, it's very time-consuming. There are very few experts, and we definitely need new tools to work with diffuse scattering. Now, let's have a look at the substitutional disorder. So the diffuse scattering from the crystal where two molecules, A and B, occupy the same place, can be mathematically presented as a product of two components. One of them is a difference structure factor squared, and the other part, which is written here as a cosine series, contains coefficients linked to the probabilities of finding certain molecule at a certain distance from another. So all this theory about that, you can find in the books of Krivoglass. But let's look at this problem from the modern point of view. So what we see for these two components, they look very different. So that means the separation of their product can be seen as a pattern recognition problem. And deep learning, machine learning algorithms actually quite good for this problem. And this is exactly what was done by Chloe Fuller and Lucas Radden. Chloe is our former postdoc. She generated more than 100,000 of artificial data sets used to educate the deep learning algorithm. And in the end, the algorithms start solving the problems. And you're welcome to download and try this software using this barcode and this address at GitHub storage area. And so the more we solve, the better it will work. Now I show you how it works with the problem of correlated arrays of quantum dots inside MOVs. So it's quite interesting problem itself to grow correlated arrays of the semiconducting small nanoparticles. And one of the approaches is to synthesize them like we built a ship in a bottle in the pores of the porous material like molecular open frameworks. Those crystals were grown by Oleg Khodrychuk from ETH Zurich, and he brought them at the beamline because they were not scattering well at the lab. So they do not scatter well also at synchrotron, but then we see why. Because there is a lot of intensity between break spots, and it comes from the correlated distribution of these clusters there, metal halide clusters. So the first question is actually what is the origin of disorder? Because solving average structure from the break data, we arrive to something which looks messy and quite difficult to see any cluster in these partially occupied atomic positions. And the second, how these metal clusters correlate. They can be randomly distributed in the space. They can show the clustering, or they can, so it's a sort of the positive correlations, or they don't like each other, and then they try to be as far as possible from each other. So different scenarios possible. Now we take this diffuse scattering datasets for lead iodide and give it to our algorithm. Within few seconds, we have a decomposition on two separate components. So this one, the one below is our form factor, and above is our correlation part. So the correlation part, you can take any part of that to find an average over many brilliant zones. you can refine the coefficient in this cosine series, and you need just few of them. From the signs already, you see it's correlation coefficients for the nearest neighbor, next nearest neighbor, etc. So it's negative, positive, negative, positive. So what we have is this. So these clusters don't like each other. So the nearest neighbor is negative, so it prefers to have empty pore close to it. If we compare calculated form factors, we see that for that we need already certain models. So we have a model of the cluster, which can be in two orientations. This is one of the versions of the disorder. It could be a cluster and an empty pore. So comparing what comes from the calculations, we see that the second case is much closer to what we have. So we can use these correlation parameters and this model for the Monte Carlo realization of the structure, and then calculated model diffuse scattering fits actually quite well to what we see from experiment. So the local structure, therefore, is based on a rule cluster like to avoid each other. If they close to each other, they in opposite orientations, but the most frequent case is a cluster, empty pore cluster, and in average they are close to each other. Appears close to each other in average structure than they actually are. This is quite important because proximity of clusters and their arrangement is crucial for optical properties of these arrays. There are many properties which have very strong dependence on the separation and also on the media between them. So these works are very, very fresh. They are not yet published, but they already presented in quite a few conferences. So I show them here. You see that they got already 3 prizes. And we are waiting now for the first papers. And this is illustration of what you could have if you also work with users on their problems and not just ignore or send them somewhere for self-education. Now, we work in the material science, and this is quite a vivid crossroad between physics, chemistry, crystallography, and there is a lot of evolution happens there, so towards more and more complicated system, multi-component systems, out of equilibrium, non-ergodic systems. On the other hand, we have evolution of research topics for our community, which goes towards processing. So we practically never solve crystal structure. That's what crystallography normally do. We try to characterize structural processes in its dynamic for more and more complicated conditions. And of course, it results in the evolution of the beamline. So in the beginning, it was a single crystal diffraction beamline. Now we do crystals, powder, and thin films in situ and operando. And hope soon we also will work with the devices, optionally in real and reciprocal space, but I cannot tell you the date for that. It's a complicated issue nowadays. But I want to mention one thing. So at any beamline, we have a physical limit of incoming flux. After upgrade of VBS, we actually have enough flux to study radiation damage. But what we can increase then, we can maximize the number of scattered photons. The most of the scattered photons absorbed by walls of our hatches. So we need a better average of the scattering cross sections. Simply speaking, we need more detectors to put around the sample. And I hope this is a principle which we will be able to realize in the next version of our beamline. Now, what I want to, my aim was to show you that diffraction crystallography at our beamline is not just a structural service, it's a complex crossfire of different components, beamline hardware, the control of the sample conditions, and management of the data, and support and collaboration with the users. And of course, the users is a main part of this equation. We're quite happy and privileged actually to have very good and motivated users. And we also try to train them. For that, we organize the schools at the beamline for the Swiss users, and where they can bring their own sample and try to see what synchrotron does for them. And at that, I thank you for your attention, and I'm open for questions.